A rectangular storage box with an open top, it's obviously important, has a volume of 10 meters cubed. The length of its base is twice the width. Material for the base costs $10 per square meter. So this looks like a question that involves cost of material. Material for the sides costs $6 per square meter. Find the dimensions that will minimize cost to build the box. State the minimum cost. Found all answers to the nearest hundredth? Well, you understand what that's supposed to mean. Okay, so there's a lot of different things we want to do here. We probably want to draw this out depending on how you visualize it. You could try starting to draw it in 3D, and then you might also want to draw the net of it. So I'm going to draw the net. That's the base. It said rectangular, so I'm making sure it looks rectangular. That's going to help me visualize what the different sides are. If I drew it like a square, I might start to confuse myself a little bit. Okay, and then here are the sides. And the only reason why you might draw it in 3D first is so that you know where the dimensions fall. In other words, this right here is my height, right? And all of these have to be the same. You don't have to mark them as the same. I'm just saying when I drew it, I tried to draw it on purpose that those flaps would fold up to actually form a box. You can't have the end flaps be longer than the side flaps that way, because that's what forms the height of the box. That's going to be important. And then go back and start looking at things like the length of its base is twice the width. So I'm going to call this the width. And this is going to be the length, which is twice the width. That actually kind of looks like I did that on purpose. It actually is twice the width, but I didn't even think about that. But again, a good reason to make sure the length is significantly longer than the width. Because now it does kind of look to scale in terms of the question, I think. At this point, you might state some of your other givens. So the volume is 10 meters cubed. There's two costs. And something else that we often do at this point is and this is kind of for yourself, but it also does help me or your reader look over your solution and follow your line of thinking. But we're trying to minimize cost. And what that does is it focuses you that you have to come up with an expression for the cost. Don't come up with an expression for the surface area of the box. The material that makes the box is the surface area. So that is what we're talking about. So why does it give us the volume? We'll find out in a moment. You need to come up with an expression for the cost, because calculus and derivatives allow us to minimize functions. So we come up with that function, put it through our calculus tools, and find out where the critical values are and figure out which one's the maximum. Sound good? Okay, so where do we start? I'm going to do this. You might do this in different ways. You might separately come up with the different expressions that you need just for the surface area. But I'm going to do this. Cost equals. So it's $10 per square meter. So it's going to be $10 times the number of square meters that make up the base. What is the base of this box? 2w times w, which is 2w squared. Very good. So that's the area of the base. Yep. It's a good idea to define your variables. I think I did say, and it is something we usually allow, if you have a diagram that's meaningful and your variables are labeled in your diagram, that can be like your let statement. Plus $6 times, so what's an expression for the sides, the material required for the sides? Well, let's take a look. It's going to be 2w times height. And then another, that's the top flap, and then another for the bottom flap, 2w times height. And then the left flap, w times h, the width times the height, and then another width times the height. No top, so I think we're done. Which equals 20w squared plus 6 times 2wh, 4wh, 5wh, 6wh. But we want this in terms of a single variable. So we want to replace that h with something. So this is where the volume comes in. Volume is equal to length times width times height. The length is 2 width and the volume is 10. So if I sub in 2w times h, I'm going to divide by 2, so I get 5 equals w squared h, and h equals 5 over w squared. Therefore, C at w equals 20w squared plus 36w times 5 over w squared. 36 times 5 gives me 180 w to the negative 1, or 180 over w. And now we have our expression in one variable. Imagine if you had the h in there. You'd have to have like a dh by dw or something. That, nope. We did that on related rates. Notice there was no related rates on the exam outline. Right? We did that in related rates, so that's different. All right, so now what? Now we take the derivative. So the max and min will occur at critical values, which is where C prime will equal 0 or does not exist. Ooh, I meant to mention this when we were doing the exam review. A lot of the functions that we look at where they do not exist is a vertical asymptote, right? And so we don't worry about that. When we take the derivative and find a place where it doesn't exist, we ignore it because it's a vertical asymptote. But there are those cusps where the function exists, it's not a vertical asymptote, but the derivative doesn't exist. That is a max or a min value. So keep that in mind. You could have a question like that on your exam in one of the other sections that just says find the derivative and state where it's equal to 0 does not exist, that kind of thing, or find the max min values in an interval. If it's a cusp, then that would be a bit of a tricky one, right? So keep that in mind. But also here, the answer to these questions tends to be where the first derivative equals 0, but technically it's both. Okay, so 0 equals 40w minus 180w to the negative 2. Moving the negative 180 over, I'm going to bring the 40 over and simplify that fraction. So 180 over 40 is 9 over 2 is equal to w cubed. So w equals the cube root of 4.5, or 9 over 2. Which is approximately 1.65, turns out. Everybody okay? Questions? Okay, we often did a check. Check the value we found and check a couple of a value below it and a value above it, probably not too far away. And both those other values were a bit more expensive, so it looks like this is correct. Everybody okay? I'm just going to scroll back up here for a minute and reread the question. Find the dimensions that will minimize the cost and state the minimum cost. So we found the minimum cost, $163.54, but I need the dimensions. So we found the width is approximately 1.65. The length is twice that, which works out to 3.30. And the height, remember, is 5 over w squared. And that works out to approximately 1.83. How do we like that? All right, moving on. Find the maximum and minimum values of the function below on the given interval and the values of x at which they occur. First thing I'm going to make a note to myself of is this has a vertical asymptote at x equals 0. It's not a sketch, so I'm not worried about all the other stuff. So maximum and minimum are critical value the critical values. Critical values occur when f prime equals 0 or does not exist. So we want to find f prime. Derivative of the top times the bottom minus the derivative of the bottom, which is just 1, times the top, so it's just minus the top over the bottom squared. 2x squared minus 1x squared is x squared minus 4 over x squared. So f prime does not exist when x equals 0, but that's a vertical asymptote, so I don't care. But I make that statement. Whenever you're doing critical values, whether it's a question like this, or the first derivative chart question, or a curve sketch, whatever it is, you always want to state that. Yep. Yeah, well, what would the maximum be if there was a vertical asymptote or minimum? I'm not going to give you a question like that. But if you got a question like that, I suppose it would be reasonable that you would have to check what the function is doing as it approaches from the left and the right, and then you would say it's an infinite maximum or infinite minimum. But the function could have, if the function approached the asymptote from the left and right and went down, then the minimum would be infinite, but it would have a maximum still. So that would be an interesting question to sort of explore, but it's not going to come up on the exam. Good question. Is that okay? Yeah? It really kind of depends on you would say the minimum is infinite. I don't know that we have a definition for that. The whole point of this kind of a question really is more the application of it, and so then the application would be, you would interpret it based on the application. Does that make sense? Okay, so let's figure out where this thing equals 0. That's where the top is 0. Which occurs at plus or minus 2. So that the asymptote's not in the interval, and x equals -2 is not an interval. You have to state all of that, and then we check the beginning of the interval, which was 1, critical values that are in the interval, which is just 2, and the end of the interval, which in this case is 10. This question, the last question where we did optimizing, these ones, it's helpful if you can punch the function into your calculator and then just change the value. Like we started doing that more when we did sketching, but it could be useful for all these ones. If you have a calculator where you can use the memory function or the memory functions or the variable functions to do this sort of thing, you could save you some time. Okay, just get those values and then interpret it. Therefore, the minimum is 4, and that's when x equals 2, because it says what's the minimum value and what's the x where it occurs. And the maximum is 10.4 at, that's not supposed to be f at 3. I guess it was counting, 1, 2, 3. At x equals 10. Don't forget to write your final statement. Any questions? All right, I want to get through one more question here because it's our curve sketch. Oh, these instructions are a little messed up, but oh well. So, you got to state all intercepts and all the things that are in this list, and your curve sketch on the exam looks exactly like this. It has those 4 criteria. And you will be given the first derivative and the second derivative on the exam as well. You just have to know how to use them. But all the 4 criteria also have to be labeled in your final sketch. So your intercepts, your asymptotes, and end behaviors, and that includes behaviors around the asymptotes, obviously. Your critical points, and they have to be classified as maximums or minimums. So you're going to do that in your second derivative chart, and then also make sure that they're drawn and labeled somehow on your sketch. And concavity, that's in the second derivative chart, and points of inflection, again, will be summarized there, but then also shown in our sketch. So let's get started because we only have 15 minutes. The intercepts. So the y-intercept occurs when x equals 0. If I put x equals 0 in, I get 0. 0 over negative 1, so 0. And that, if you have a y-intercept at 0, you got an x-intercept at 0. Don't make that mistake. Try to draw a graph that has a y-intercept of 0 that doesn't have an x-intercept of 0. But often people miss that in these kinds of questions. And this one only has that single intercept. One x-intercept and it's at 0. Okay, asymptotes. Vertical asymptotes are when the denominator of the function is equal to 0. So x equals negative 1 and x equals positive 1. And then you have to decide, does this function have a horizontal asymptote or an oblique asymptote? And this one's oblique. So we're going to figure that out after. We'll do the behavior around the vertical asymptotes first. Tell me if I'm going too fast, but I want to get through this. So how do I do the behavior around vertical asymptotes? I say the limit as x approaches -1 from the left of the function y. The limit as x approaches -1 from the right of y. The limit as x approaches +1 from the left of y. And the limit as x approaches +1 from the right of y. So again, this is where it can be really useful to punch the function into your calculator. And then just put a number right below -1, so -1.001. Put that in for A. Evaluate it. This one, I believe, is -infinity. This one's +infinity. -infinity. Positive. It takes a minute to do this, so we're going to save that time. I'm just going to do it. But that does take a couple minutes to do this, right? This is a long process, these sketches. Okay, so that's done for the vertical asymptotes. I have all the behavior. There's 2 vertical asymptotes. You've got to have the behavior from the left and the right of both. For the oblique asymptote, do you remember what we do? We divide. And in this case, this is kind of a tricky one in a way. It's x squared minus 1. So this is actually like a trinomial kind of, but it's got a ghost term in it. So I have to do long division. So x squared plus 0x plus 1 dividing into, and look at this is kind of wonky, x cubed on top. So x cubed plus 0x squared plus 0x plus 0. Yep. That's the bottom. Oh, sorry, it's -1. You're right. That's what you meant. Sorry. I don't know why it became +1. Okay, so x squared goes into x cubed, x times, so that value that I get there, x times x squared, gives me x cubed. So when I subtract these, I get 0. Then I multiply it by every other term. And so x times 0x is 0. X squared, and x times -1 is minus x. Then I subtract. So x cubed minus x cubed is 0. 0 minus 0 is 0. And 0 minus -1 is positive 1x. Bring down the 0 plus 0. This is also a 0. This is a little bit strange too. X squared goes into 0 times. Once you have a remainder of 0, you're kind of done dividing, right? So do we need to continue going through this process? I suppose not, but this is what the process would look like. So then 0 times 0, I get 0, 0, 0. And I'm done. Actually, we're not all the way done. I'm lying. Because when I do that, I get x minus 0 is x, so I do have to finish that because that's part of our remainder. It doesn't divide evenly. If it did, then this whole thing would look really different. Okay, so this is just x, but now I'm done. So I'm going to make my statement y equals x plus x over x squared minus 1. So my oblique asymptote is y equals x, and my remainder function is x over x squared minus 1. testing behavior around oblique asymptotes, that's the same as around a horizontal asymptote. So it happens when x gets really big positive or really big negative. So I'm going to do r at negative 100 and r at positive 100. R at negative 100 gives me something that is less than 0. It gave me a negative. Therefore, I'm below the asymptote. And R at 100 gave me a positive, so I'm above 0. Therefore, I'm above the asymptote. I'll remind you, this is something that people get mixed up between vertical asymptotes and horizontal asymptotes and oblique asymptotes, exactly what the test looks like and exactly what your conclusion should be like. When do you only have to check if it's positive or negative? That's all you care about. When do you care about the actual value? Depends on what you're doing. So make sure you've got that clear. We okay? All right, so that was just the asymptotes. I've done the intercepts, I've done the asymptotes. Now we have to do the critical values and the points of inflection. So y prime equals 0 or does not exist. We're given this x to the 4 minus 3x squared over x squared minus 1 all squared. So it does not exist at x equals plus minus 1, but those are vertical asymptotes, so that's done. How am I going to solve this one? I'm going to factor it. So y prime equals 0 at x equals 0 and plus or minus the square root of 3. Those are critical values. Now let's do points of inflection. Y double prime equals 0 or does not exist. Y double prime equals, this one's given to us in factored form, which is nice, x squared plus 3 over x squared minus 1 all to the 3. So y double prime does not exist at x equals plus minus 1, but those are vertical asymptotes. And y double prime equals 0 at x equals 0. And that's it. Just 0, because the x squared plus 3 doesn't have any real solutions. Five minutes, oh my gosh. I'm gonna move this out of the way somehow. Okay, so I got to do my chart. Chart includes vertical asymptotes because concavity can change, or if you're doing a first derivative chart, intervals of increase and decrease can change. Whether a function is increasing or decreasing or concave up, concave down can change at an asymptote, right? So we start at x less than negative 1, then at negative 1, from negative 1 less than x less than 0, I believe is our next one, and then 0. 0 less than x less than 1, 1, x greater than 1. Again, this is where I would put the function into my calculator and I would start punching in the numbers, but I'm going to do this for us. This one's negative. This does not exist because it's an asymptote. This one's positive. This one is 0. Lots of stuff happened there. We had an intercept. We had a point of inflection. We had a critical value. This one is negative. This one's an asymptote. And this one's positive. So I've got concave down, vertical asymptote, concave up, point of inflection, not a max or a min. It's a critical value because has a horizontal tangent line, but that also occurs where you got a twist. Concave down, vertical asymptote, concave up. So I have a critical value at negative square root of 3. That's in this top interval. It's concave down. That looks like this. So I have a local max at negative root 3, and it works out to negative 2.6. Yeah, that's right. I got a POI, I already know that one. That's 0, 0. And I have my other critical value is positive square root of 3. So that's in this last interval, which is concave up, which looks like this. So that's a local min. And I believe that's positive 2.6. Do we have enough time to actually do our graph here? So this is going to be A, B, C. I'm going to do it really quickly. Maybe we'll do a better job later, but okay, so I've got asymptotes at 1 and negative 1, and I'm going to label those. Checking my behavior inside those asymptotes, it's going to positive, approaching this one from the right. And then there's my intercept and my critical value, horizontal tangent line, and a point of inflection. Notice how that's concave up. And then afterwards it's concave down and approaches the other one. Approaching the other one from the left, it's going down. I have my oblique asymptote. Y equals X. You got to know how to graph that line. And then my function, I shouldn't have drawn this in. Okay, and this one just goes like this. And this one just goes like this. And so we see that we've got our minimum here, which was point C. This was point B, I believe, and this was point A.